All right, welcome back. Today I'm going to tell you about some work we did with Mingji Liu and Yi Lin, two students that work in my group with me, on how we use machine learning to simulate acrolein-induced surface segregation and aggregation of silver-palladium alloys. So to give you an idea why this is a tricky problem, let's scroll down to the main graphic here. And what I show in the right here is a example of a model surface where we have a lot of little gray balls that might be the silver atoms, some blue balls that are the palladium atoms, and they're far apart, so they're in the dilute limit where they don't interact with each other. And then we have some adsorbates around, and we would like to see what could we simulate to tell us what is the most stable or most likely configuration of all these atoms. And the problem with this is DFT is too expensive to do a simulation this large, and there are also so many different configurations to consider that we can't do enough DFT calculations to solve this problem. So what we want to do instead is to use Monte Carlo to sample this, and that only shifts the problem somewhere else, because to do Monte Carlo we need to calculate the change in energy for all the different, as we change the configurations. And so we have conventionally got those changes in energy from DFT. And again, this is just too big. So what we would like, what we have done in the past is use machine learning to build a model that would calculate those changes in energy for a slab like this. But we would use a very large slab, like 10 by 10 by 15 layers. So something like 1,500 atoms. And then we could do it at a constant concentration, where the bulk in the middle concentration would sort of fix the chemical potential. And that works, but those big slabs are expensive and limited in the number of concentrations we can look at. And instead, in this work, we want to use small slabs like this. And the problem with these, of course, is that when you start changing silvers and palladiums, you change the composition. So we're going to switch to a semi-grand canonical approach where this slab is free to exchange with the bulk reservoir, and we can use this chemical potential to tell us what is the cost and energy to determine whether it's a favorable swap or not. And then we need to account for adsorption, which can impact the segregation. So we need to have a way to estimate what is the change in energy from adsorption, what is the change in energy from this exchange, and when we combine them, what is the net effect on the configuration. And if that's an efficient process, then we use Monte Carlo, and we can run thousands and thousands of steps to find what is the most likely configuration. So to do this, we need a couple of machine learning models. So we need to be able to calculate what is this chemical potential here as a function of bulk chemical potential over here. We need a machine learning model to tell us what is the energy of a slab when we change the composition, and we'll need a machine learning model to tell us about these adsorption energies. So let's take a look at a few of those pieces. So the first kind of machine learning model we'll look at is a single neural network for the silver palladium bulk and for the slab potential energy surface. And this is the regular single neural network I told you about before. And we train them in the normal way that we've described before. We use Baylor-Parnell symmetry functions to represent the atomic local environments and the single neural network architecture. And then we just train that until we can use the neural network for that to give us the bulk energy and the slab energy for any configuration of interest. For the adsorption energies, we do something a little bit different because we have a large molecule here, acrolein, and there are lots of ways it can sit on any given site. And so what we did was generate a pseudo-adsorption energy that is close to the lowest energy of all those configurations we know of, and that we learn a pseudo-atom fingerprint for that we can generate from the Baylor-Parnell symmetry functions, and then we develop a machine learning model that is pretty good at predicting those. I'll show you what it means. But we found that with 287 different geometries, we could get a pretty good model that we think is good enough for the absorption energy. And then finally, we do the semi-grand canonical Monte Carlo simulation, where we can fix a chemical potential for the bulk reservoir to exchange with, and we have a fixed number of acrolein atoms, our molecules on the surface, at about 1/9 of a monolayer. Okay, so how do we get the relevant quantities? So we have to calculate the silver palladium chemical potential. We do that by a Monte Carlo simulation where we fix the chemical potential of interest and allow atoms to exchange until the energy is constant, and that gives us a mapping of chemical potential to bulk composition. Then we can do similar things with the bare slabs. So we can, once we fix a chemical potential, we can allow the bare slabs to exchange atoms and see what the eventual concentration in the surface is. And finally, we can do the same thing where we add energy of the slab plus absorption plus the chemical potential, and that gives us the full set of conditions that we're interested in looking at. All right, so let's look at first just the segregation under vacuum. So and the influence of absorption. So here, this figure shows let's see, 16 different acrolein configurations on pure silver, 1 palladium, 2 palladiums, 3 palladiums, and 4 palladiums that are in the surface. And what you can see is the various contributions. So palladium coming to the surface is always unfavorable. So palladium has a higher surface energy, and it would much prefer to be in the bulk. And if we look at the absorption energy, it is always favorable. So acrolein always wants to sit on the surface, and the sum of these two things is what leads to adsorbate-induced segregation. And for the most part, acrolein absorption is pretty weak, and so it, for the most part, does not offset the segregation energy, except for this one configuration where you see a little bit of stabilization. Now, this is the reason why we can't do DFT. So these are all DFT results, and 15 out of 16 aren't favorable. And there are a bajillion other ways that acrolein could sit down, and we don't have the capability to calculate them all. There are also a bajillion other ways to have arrangements in the surface that we just aren't able to use. And so we will get to why and how we get a machine learned model to replace this. All right, so this is just showing you what the parity plots of our single neural networks look like across the whole energy range. We see pretty good parity, pretty small errors of 1 to 2 millieVs per atom, and we look at this with a variety of different seeds, random number seeds, so that we can check and make sure that it doesn't really matter how we did the training. It's all pretty good. This is the same for the slabs. So these are the results for the bulk alloys. These are the results for the slabs. So this is mostly just showing you that we have 2 neural networks, one for bulk energy, one for the slab energy, and we think they're pretty good. For the absorption energy, we did something a little bit different, but I'm going to skip that until that figure comes and get to what the bulk chemical potential ideas mean. And now that I said that, here is the absorption energy model. So what we did here was look at a pseudoatom, which is just putting this red dot here, and then we calculate a fingerprint vector for that local environment, and then we have a set of different acrolein geometries that were on that site, and we take the lowest energy one, the most stable one, and use that as our label, and then we fit a machine learned model that relates the fingerprint to that absorption energy, and this is what the data kind of looks like. So it doesn't look like wonderful in terms of the parity plots I showed you before, but there's a lot that have a very small error in here, and then there are a couple that are outliers, but these are bridge sites and hollow sites, and then these ones are like not quite as common to be seen. And maybe what's important is that they're all negative, right? So minus half an EV to minus 1 EV, they're all negative, and we're not getting the wrong signs anywhere. And most of the errors, it turns out, are fairly small. So this is what we have. The only alternative we have to this is to actually calculate all of them, and we don't have the DFT resources to be doing that, so we use this kind of simplified model that will allow us to proceed. All right, so let's look at the bulk chemical potential. So this is a number that we choose, and there are some bounds on it, but if we pick one of these numbers, then this will map onto a bulk concentration. So up to about this point, maybe 2.55, the bulk chemical potential is basically linear in the palladium concentration. And that is mostly a reflection of the fact that this is the dilute limit, where palladiums don't really interact with each other. And once you go above this, you start to see some nonlinearity in there, and this is where you start getting into the concentrated regime, and we're not super interested in that regime. So once we have this, we can allow a slab to exchange atoms with it, and this chemical potential tells us what the change in energy is when we do that. And so if we do that with a Monte Carlo simulation, what we see here is the first layer is hardly any palladium, right? Silver goes to the surface almost exclusively up to about 11% or so, 10 or 11% palladium. Then you start to see a tiny bit of palladium in the first layer, but you see quite a bit in the second layer. So the second layer is concentrated in palladium compared to the bulk concentration, and that's also pretty well known. It's not that the palladium atoms just go deep into the bulk; they just have to go into the second layer for it to disappear. And that's important, especially when there are adsorbates around, because it's not a far distance from the second layer to the first layer. If we add acrolein, then we see a very different story. So now in the first layer, even at the lowest chemical potential of say 5%, we already see more than 10% palladium in the surface, and that just increases as we go. So at 8 or 9% bulk palladium, we see more than almost a quarter, 25% of palladium. So the acrolein induces the adsorption and causes, even in the dilute limit, concentration of palladium in the surface. So the question then is, how far can you go if you want to be in the single atom limit? And what you can see is if you go very, very dilute, you will just have single atoms, but not very many of them. And so what this figure shows is that we are 100% single atom limit in the on top site up to about 6 or 7% bulk palladium. And then after that, what you see, and down here you see no hollow sites, which means that there are trimers of palladium, and no bridge sites, which means there are dimers of palladium. And so again, around 7% here, that starts to go from 0, where you see an increase in the number of dimers. And what we know in catalysis is the single atom limit is good for high selectivity, and once you get dimers, then you lose the selectivity because of the palladium-palladium interactions. So the end result of this work is we had to make a lot of compromises in how we would simplify and approximate all of the interactions for alloy segregation, for adsorbate induced segregation, and when we put it all together so that we can run the Monte Carlo simulations, then we finally get to a design goal here that says, at least within the limits of the approximations we made and the limits of the accuracy of the DFT model that we used, that we don't want to exceed about 7% palladium in the bulk for the surface that we looked at before you would expect to start to see dimers and trimers and loss of single atom activity. All right, so that's basically it. Tomorrow I'm going to give kind of a more formal presentation that isn't me just walking through the paper, and I'll show you how all the 3 papers that I've talked about this week come together, so that you can see in more detail how it works. So thanks for listening, and I'll see you next